Thank you. Great. Can everyone hear me if I speak like this? Yeah, okay. So, yes, that's what I'm gonna talk about. Thanks very much to the organizers for inviting me to this wonderful conference, giving me the chance to speak. I'm gonna talk about what it says here, and the picture on front of my slide is sort of a summary of what I'm gonna talk about. So if you understand that, you understand everything. I'll say what I mean by that, of course. But first I want to acknowledge my collaborators. This was work done with my grad student, Wei Li, and my postdoc, Julia Fardelli, was really quite excellent. Can't say enough good things about her. But let me get to the point. So I want to kind of start by creating some drama. What we would like to do, our goal is to describe the 3D O2 model holographically. And normally we say this can't be done. Normally there are certain things that we think a model, a CFT should have to have in order to be described holographically, and this doesn't have them, so you shouldn't be able to do this. So let me start by saying what one of those reasons is. I think the most important one is basically that the central charge is small, and that really should kill you. Why does that kill you? It's because on general grounds, the central charge sets the separation of scales between the Planck scale and the ADS scale. And if you think of ADS as being like a box of size LADS, that's the longest scale around. The Planck scale is the same scale, so all scales, gravity is strongly coupled. So you're done. You just can't do anything unless you can solve strongly coupled quantum gravity, whatever that means. You're just dead. So that sounds bad. Sounds like we should just give up. But that would be a very short talk. So why do we actually have some hope? And the reason we have some hope is because ADS isn't actually a box of size LADS. That's just some, intuitive way of thinking about it. But of course, ADS has an infinite amount of volume. It's actually infinite in size. And so the question is, how do you actually get to take advantage of all that extra volume? Right? How do you get to take advantage of those longer length scales? And the way you do that is you take things and you give them a very large angular momentum. And that starts to spin them up, and they start to move farther and farther out from the center of ADS. And as a result, you get an additional much longer length scale. There's simple kinematic fact that the distance you move from the center of ADS grows logarithmically in the angular momentum. And so now we have a big separation of scales, and now we have a chance to build an effective theory. And that's basically the idea. Okay, so the UV cutoff of the effective theory is the ADS scale. There's going to be an infinite number of irrelevant operators up here, where everything breaks down, and we're going to describe what happens in this region. Okay, so that's the idea. All right, and why is this? Let me just tell you a little bit about sort of how to think about the setup. So the reason why large J gives you large angular momentum, gives you a large distance, is a kinematic fact. It's just the ADS geometry. The curvature of ADS space is sort of like a potential well that pushes things into the center. And as you know from literally when you were in kindergarten, I'm not even joking this time. If you spin things around, then they move out if they're sitting inside a potential well. So to prove to you that you knew this since you were in kindergarten, here's a video I took at the Children's Science Museum in Boston. That I went there with my son, who is in kindergarten, so he knows this fact. And you have balls in a potential well, and the well pushes them towards the hole. Why don't they fall down the hole? It's because they're spinning. Okay, the angular momentum creates a centrifugal force which pushes them out. Okay, all right. So you've all known this for a very long time, and then they do it. There's friction in the system. It's not. How do I stop this video? All right. Eventually, this figure it's not a ADS it has less friction. All right. Very good. That's the idea. And you just do a short calculation in ADS. The distance that they move from the center, if they have angular momentum J, is a distance which is log of J. Yes.
Okay. That's going to watch out. It's like 1 hour out or
this is the geodesic distance from the center.
No, but when you write it 1 over J here in this diagram, and if I look at the diagram, I would say that it's like a Coulomb law. I mean,
it's a Coulomb law, but in ADS.
Yeah.
exactly. So, I'm getting to that. Let me get to it right now. So, I'll go back and talk about this in a second, but to answer your point, you can ask, what is the Coulomb potential between these balls? All right, so part of why I like showing you this video is you all sort of instinctively start to create in your own minds the effective theory for these balls. You can't help yourself, you just have to do it. And you're familiar with the fact that these balls have a very small effect on each other, right? They're circling around, but if you remove 3 of the balls, the last ball does more or less the same thing it would have done without the other balls. They do exert a small force on each other. All right, one of those forces is the gravitational Newton's force. It's extremely small, but it's there. In ADS, you can calculate it, actually not just gravitational exchange, but on any exchange of any particle in ADS, the propagator falls off exponentially as a function of distance. This is different from flat space. In ADS, it falls off exponentially. All right, and the coefficient here, I call tau. Tau stands for twist. And the point is every field in ADS is dual to a CFT operator in the boundary. The CFT operator has some dimension and spin. Twist is just dimension minus spin. Okay, and that controls how fast this exponential fall off is. All right, and so you can just do a very short calculation. You can ask how much these balls affect each other if they have angular momentum j. Their distance is log j. The contributions from exchange of a particle with twist tau is e to the minus tau times the distance. You can do it in your head. The correction to their energy is 1 over the angular momentum to the tau of the exchange particle. Okay, so it's very small if j is very large. So they barely affect each other if their angular momentum is very large. Okay, so even though these balls are strongly coupled, they're made of, I don't know what billion bars are made of, porcelain, maybe something else. I don't know. It doesn't matter, is the point. You don't have to model them. All you have to know is that they couple to this exchange with some coupling constant, and that's enough to compute what the correction to the energy of the 4 billion ball state is. Okay? Yeah. Yes.
Taking both j to be large and tau to be large?
No, I'm not taking tau to be large. Tau, for instance, for the graviton, tau is d minus 2 and spin 2. So tau for the graviton is order 1. Okay, but it doesn't matter. J is the big number, not tau. Okay.
But this is the left-hand side, that the heuristic approximation to the propagator.
That's one way of calculating it, but this is in the limit where chi is very large, you can approximate it with the geodesic. Yes, that's right. Good. Okay, so here's the idea of the effective theory. Step 1, you choose your twist cutoff. It can be low, it doesn't have to be big, we can take it to be 2. And usually in this talk, I'm mostly going to take it to be 2. Then what we do is we divide all effects into long distance effects and small distance effects. So what I mean by that is we keep all the potential, the long range potentials from exchanges with tau below our twist cutoff. Okay? And as long as we do that, as long as we keep every exchange with tau below 2, for instance, then that means we get all corrections up to and including 1 over j squared. Okay? We don't get the 1 over j cubed, but we get the 1 over j squared from these exchanges. And then the last step is just a standard effective theory approach. So up to this point, it's just large spin expansion. And then the last step is where we bring effective theory into it. And there are, at finite j, there are a bunch of short distance effects, which we just add in local counter terms to match. Okay, so they're going to be, in addition to these long distance exchanges, there'll be short distance effects, which are completely captured by local terms in the effective action. That's the construction. Okay. So just to show you an example to convince you that there's actually some quantitative accuracy to this thing. We applied this last year to the O2 model. The O2 model is nice because there's a conserved charge. Just makes things cleaner. You can count the number of particles just by counting the charge. And here is the circles are the bootstrap results, and the triangles are what you get from the effective theory in ADS. What do I mean by that? The effective theory is a holographic bulk model with a photon, a graviton, and then we also include a state with dual to the epsilon operator, has dimension 1.4. And if you only include those three things, you do extremely well at large J, which you had to. It has to work at large J on general grounds. But what's sort of remarkable about this is it works extremely well down to small j as well. In fact, all the way down to j equals 2, you have, I think, like 1-2% errors. And then, I didn't put it on the plot, but if you go down to j equals 0, you just get totally the wrong answer. J equals 0 doesn't even show up on this plot, it would be way up here. And the way I want you to think about that is j equals 0, now the two particles are right on top of each other, there's no separation at all. It's very sensitive to the strongly coupled short distance effects at the ADS scale, but you just fix that in by putting in a local counter term. So you stick in a local counter term, this only changes the j equals 2 energy. You choose its coefficient, you go to your bootstrap results, you ask what is the dimension of phi squared, you put in what is the dimension, and it's 1.2, and you stick in a coupling here to match that. And now you get very high accuracy for two particle states for all j, from 0 to infinity. Okay? Yeah, Clay?
How did this debate develop in trying to solve the bootstrap, truncated set of operators?
How does this, okay, especially how does this relate to just trying to solve the bootstrap with just a truncated set of operators? You mean if you were to literally truncate the conformal loss?
You have your bulk model with A, H, and epsilon, maybe I should try to do a truncated bootstrap with just J, you can do whatever.
You just do a truncated, you would also, so one thing that, yeah, you also have to include, you'd also have to include double trace operators as well.
Double is like for.
Yeah. That's an interesting question. If you were to really literally try and solve the truncated bootstrap equation, I don't know how you would do. What I can tell you, which maybe might satisfy you, is that if you just use the inversion formula, you will get the same results. So what the ADS exchanges are doing at this level, the exchanges are what they're doing is they're capturing the Lorentzian inversion formula contribution from the J mu exchange, the T mu exchange in the end. So the fact that that works well, so that the history of this is actually before that, the large spin expansion was compared by Fernando and Sasha, and they saw this, and then the inversion formula does slightly better, but qualitatively the same. And so this is the ADS model is sort of at this level, it's just capturing that. Okay.
So the fact that it works for j equal 2 is quite surprising because the scale separation you showed us.
It is quite surprising, yes. It's quite surprising that it works so well down to j equals 2.
At
Yes.
j equal 2, it's almost like we're going back to the L prime.
Yes, that's right. Yeah, so hold that thought. I'll talk about it at the end. For now, let's just, I have some words to say maybe about why it works so well at j equals 2. For now, just it's, just be surprised. Okay, so now what's the point of this? There's no inversion formula so far for higher particles. But we can go look at higher particle numbers, and now things start to get really interesting. Much more interesting than 2 particles. And that's because when you have 3 particles, you have many different configurations you can do at the same spin. 2 particles, there's really only one thing they can do. Once you know that once you fix to the center mass frame, the whole thing is totally fixed. For 3 particles, you can have different configurations, anywhere from 3 particles being sort of separated by equal distances to 2 of them being very close. And so in this configuration, where they're all separated as far from each other as possible at large J, you can calculate the effects of everything because it's just long distance effects and they're weakly coupled. But in this configuration, which is the opposite, you can't. Now these 2 particles come very close together and now you're sensitive to short distance effects. And so what do? It seems like you're in trouble. You have to somehow worry about the short distance effects. But notice we already did that. So here's the point I really want to emphasize. We don't actually have to do anything new. We already solved this problem on the previous slide. Where you have 2 particle states, when they come close together, we already completely accurately modeled all 2 particle states by adding this extra contact term. And so we've taken into account those short distance effects. So if you just take the Lagrangian I showed you on the previous slide and you do nothing else, and you go out and you compare and you calculate the eigenvalues of that Hamiltonian, this is what you get. Most of these are not known from the bootstrap, but some of them are, and you get an incredibly good match. Okay? Again, to maybe 2% accuracy. Okay. All right. Yeah. Okay.
How common is it for particles come across each other?
Sorry, what?
That is,
Mhm.
with particles coming across each other.
In a typical state, no. So the question is, in a typical state, will the two particles come close to each other? And the answer is no. In a typical state, most of these states, the particles are not close to each other. Most of the states, you don't really care about this local interaction. But for some of the states, the ones that look like this, they do come together, and then you get a big contribution. You can, so the question is, shouldn't you think of this as a new double trace? Yes, you absolutely should think of it as not a new double trace, it's the same old double trace. It's the spin zero double trace by squared operator, which has dimension 1.2, which we know from the bootstrap. Great. Okay. So, okay. So that was the prelude. No, if that's all you get from this talk, that's fine. But what I wanted to tell you about now is we really wanted not to do something which is, this makes it sound like maybe this is kind of phenomenological. What we want to do something is not just accurate, but something which is systematically improvable, right? The idea is we want to be able to know what the rules are so we can keep making it more and more precise. And we stop because we get tired, not because we don't know what to do. Okay, that's the idea. And so in order to really test out how to keep going, what all the rules are, we need some situation where we have a ton of data to compare to. And so we looked at the O2 model in the 4 minus epsilon expansion. All right, so as you all know, in the 4 minus epsilon expansion, there's a perturbative fixed point because of the one loop beta function. And so in principle, you can calculate everything in this expansion to any order that you want. And so the idea is you have some set of inputs from the epsilon expansion, which you use to fix the parameters of your effective theory. And then you go out and you use the effective theory to calculate everything else. All right, so there's just one quick slide on what's known about the epsilon expansion for multi-particle states. Obviously, there's been a ton of work for 1 and 2 particle states, but for higher particle states, there's much less. The most comprehensive that we found was work by Carnegie in the 90s, where he calculated the 2-loop RG transformations of the operators. And you can take this matrix and you can work out the anomalous dimensions of multi-particle states for any charge you want. So that gives us a lot to compare to. And so what we did is we said, okay, let's start with the same philosophy. We're going to write down a low twist particle exchange, which I'll call that bulk field phi star. And we include a contact term. So here are the vertices in our effective theory. There's the exchange and the contact term. And you go off and you say, well, I'm going to tune this one. There are no free parameters because the OP coefficients are known and you can fix them. And so we say, well, let's tune this so we match to the dimension of phi squared. So phi squared is given by these numbers. You do a calculation, you find that the prediction from the effective theory is this, and lambda is a free parameter, and you need to choose lambda to be 1600 pi squared over epsilon squared. That's huge, seems very bad, seems like the bulk is strongly coupled and you can't do anything. But of course, the point is that we're not going to compute everything in the bulk. We're only going to be computing the contributions from particles which are very far away from each other. And if they're far away from each other, this contact term has a very small effect in its order epsilon. For all particles which are far away from each other, the contribution from this is tiny and perturbative. Okay, so we're only computing the subset of the theory, which is where the effective theory works, where it applies. And so order epsilon, this is the Hamiltonian. You can just write it down. It's a 2-body operator, 2 A daggers and 2 A's. And this is exactly the same thing you get from the 1-loop results for the dilatation operator. It's the exact same expression. So it's the same Hamiltonian. So all of the states are automatically the same energies at order epsilon. So it's a complete match for any Q. And one thing that's just want to emphasize, one of the reasons, even if you don't care about effective theory, studying multi-particle states in the Hamiltonian framework is much easier than studying it by doing correlators. If you were to try and compute multi-particle state anomalous dimensions using Witten diagrams, you have to do a 6-point function or an 8-point function. Those things, I guarantee you, they're hard. And there are a lot of work extracting all the anomalous dimensions. Whereas if you have a Hamiltonian, We love Hamiltonians. You just stick it on your computer. It's a big matrix. You type eigensystem, you hit shift enter, and you get all the eigenvalues. Okay, so Hamiltonians are extremely useful for studying the entire spectrum of multiparticle states. Good. Okay, so this was order epsilon. Let's go to epsilon squared. All right, order epsilon was very simple. Maybe it was too simple. Maybe we got lucky that it worked. So let's try and see what happens at order epsilon squared. We're going to apply the exact same strategy. We're going to look at the, we're going to catch all the large spin behavior by keeping the field with twist 2 or less. That's going to give us all terms up to 1/j squared. And then we're going to capture all the small spin behavior by adding local terms. So what new exchanges do we need to include at order epsilon squared? There's only one new low twist guy with twist less than 2. That's phi, which has twist 1, dimension 1. And so we need to include it. And so you have to compute this diagram. You can just see by eye, it's a 3-body term, 3 creation operators, 3 annihilation operators. And you go ahead and you compute this diagram. But there's a subtlety, which is that actually, if you just do that, you get it right. The reason is this diagram includes too much. So let me try and explain that. This was something that took us a while. We were confused about for a while. But the reason why it computes too much is easy to understand if you think about what you're doing in old-fashioned time-independent perturbation theory. This is a second order diagram in 5 and 4. So how would you compute the energy levels in time-independent perturbation theory? Well, you all memorized this formula. You were forced to memorize it at some point. And you know that when you sum over the intermediate states, you don't sum over everything. You don't include the intermediate state, which is the same as the external state. All right, you all learned this formula at some point. That's already been sort of included by the fact that you're diagonalizing the rule. So you actually need to subtract that out. In fact, if you don't subtract it out, that energy denominator is 0, so you get infinity. And in fact, if you just go out and you just compute this diagram, you do get infinity. The integrals diverge. All right, and so what you have to do, the way we did it, is we took delta phi slightly away from the true physical dimension. We calculated everything. We subtracted the 1/0 term in time-independent perturbation theory. Those divergences exactly cancel when you take delta phi back to the physical domain. Okay, so we stick that in. Now this is our new order epsilon squared Hamiltonian. We just have this extra term here that we didn't have before. And indeed, you go compare to all of the CFT data and you find you get an exact match up to 1/j cubed. So you match 1/j, 1/j squared, and then you get a mismatch at order 1/j cubed. Right? So for example, here's one particular operator. Here's the exact answer, here's the EFT answer, and the difference is this exact expression, which starts at 1/j cubed. And that's true for every single state. Okay, so let's go further. We can take the twist cutoff higher and let's try and capture the 1/j cubed terms. And for this we need to include a twist 3 exchange. And naively, there's a twist 3 exchange, phi squared, phi star. But if you think about it a little more, that's not actually a primary state. Because of the equations of motion in the boundary theory, that's actually descendant. So there's actually no phi squared phi state. So there's nothing to add to fix this up. What went wrong? And the problem is actually the opposite. It's not that we need to add something, it's that we had something there we need to subtract. And the reason is the effective theory starts with just weakly coupled phi. The effective theory has a phi squared phi state in it, because it just starts with the usual Fock space plus weak interactions. And that state, it doesn't know that that state's not supposed to be there. It's a low spin, strongly coupled state, and you're supposed to completely remove it. And so you can sort of understand, if you think about this diagram here, you think about contracting the legs in different directions, and you cut through the diagram, you can kind of see that it's a phi squared phi state. So you actually need to remove it to get the right answer. So what we actually do is subtract this. I don't know if it's helpful to think about it. I like to think of it as like a ghost, because you're kind of like removing redundant extra degrees of freedom. And now the magic is you not only get up to 1/j cubed, you actually get the exact expression for all states at epsilon squared. So here is all the q equals 3 states. All of them are exactly the same as what you get from the 2 loop results in the epsilon expansion. For q equals 4, you get an exact match for all the states. And we checked up to 6 particle states, you just completely reproduce the entire spectrum at order epsilon squared for all particle number. With this very simple multiple. Okay, so that's all I wanted to say. There's some things that I think are interesting in the future, but let me just leave you with this. I went in with this quote, sort of reminder of why we do what we do, looking at the beauty and wonder of the natural world for its own sake. Thank you very much.
Yes, so basically you could have a set of geodesics that are always part of each other, and you could do an effective geography and get
You could, yes, so the question is, couldn't you just hold the particles by hand far away from each other? And indeed.
have a particle oscillating like this, and the other oscillating like
Yeah.
out of phase, then the geodesics are always part of each other.
That's a good point. Yeah, so yeah, aren't there more general configurations than the ones we considered? Aren't there other ways to take particles far away? I think it's true. So you could probably capture a more general set of
Effective
states.
theory of geodesics.
Yes.
that are powerful, you know.
Yeah, I think that makes sense. Victor?
So you said you manage these things numerically,
Yes,
but you don't, but you say it's exact, like you don't understand analytically why they should match.
we don't understand, so, yeah, exactly. So the thing that we're matching is this RG transformation, which is at 2 loops is not a Hermitian matrix. He even says this in his paper, but we numerically find the eigenvalues, and we knew our Hamiltonian is Hermitian. We numerically find our eigenvalues, and then we make a table, we calculate it out to 20 digits, and they're exactly the same.
But no diagrammatic understanding why your idea is diagram. It's
No. I mean, we like, nothing beyond, you can sort of see like the number of particles coming in and coming, you know, get 2 body terms, 3 body terms, you can see it, sort of see it at that level, but the actual matrix elements, they're different bases. So this is in a different basis from our end.
I also have a question. So, in one of those slides, you show that there is a parametric separation between your ADS land scale and your IR scale,
Yes,
and difference was log J.
yeah,
But then your power counting was in J, not in powers of log J.
yes.
So how does that come about?
It's a great question. What's the right way to do the power counting? And the level at which I understand it is the power counting is, there's some twist and the corrections are one over J to the twist, so it's a little different. Yeah, that's the power counting. Like, you might naively have thought the power counting should be in power to distance. But I think it's because of this fact that at very large distances, the propagator shut down exponentially. Sylvia?
You gave me no insight into how the ADS appears on the ADS space and the.
You're getting a new insight into how the ADS space appears. You mean sort of like how space is reconstructed from entanglement? Well, from our point of view, it's that it builds in symmetries of the problem. Standard thing, that it builds in problem symmetries. So the Hamiltonian is the dilatation operator. No, it's a little more than that. No, sorry. It's a little more than that. I think it's also the fact that you could have tried to build a large spin effective theory purely in the lower dimensional in field theory space. And I think what ADS is giving to you, there is some magic there, which is that you get a local effective theory. At least, you have local interactions, and then you have these long distance exchanges, which are local in the sense that the vertices themselves are local. And so I think, yeah, there is a good question. Why is it that local interactions in ADS sort of build in the right properties?
That hasn't been understood in detail.
No.
Neither effective theory.
No. I mean, yeah, it's, it's related to the fact, it's related to this fact that the if you include this propagator has the sort of right dependence. And so the fact that things are pulled apart in ADS and they're local in ADS is the right physics. But yes, it hasn't, I feel like.
Have you ever looked at papers that study duality between O and O?
Yes, yeah, those are.
There people are arguing a lot about whether the
Yeah, you think there might be some insight into why it's local?
You started to play this game, which is better to find the best case, to get all the remember that there are
Yeah.
built up and,
I agree. In some ways, the ambitions there were a little different. There, they took a large end limit, so that all the interactions were by construction and suppressed by one over n.
so we can look at the price, but
Yes.
I don't think that you.
I mean, yeah, like I don't think this theory is fully local either, in the sense that, the story I'm trying to tell is that it's just totally non-local up here at the ADS scale. Right? It's only local on these scales.
Right. Okay, well, last question.
So, like, is there like something like a three-part or like, but what?
Is there a 3-particle contact term? Yes, fantastic question. Why didn't I have to, I told you the story that we had to keep adding contact terms to fix up the small spin. So there's something we don't understand. There's some magic, which I took out because I didn't think I was gonna have time for it. But in fact, we do not have to add a 5 and 6 term. We don't know why. You compare to the CFT data, you ask what the coefficient of 5 and 6 is, it's 0. In the effect, I don't know why that is. Sylvia?
Computer you time, you think much math so far, or loops important or also not?
It was all 3 level. So, yeah, the loops will only contribute a higher order. So I think there's more to learn by going to epsilon cubed. This was already, not so easy, but yes, I think new effects will show up better.
All right, I will be 10, 3 and 1.